you online and of course some of you in person. And so the test will be open book, and I'll have it available online through Gradescope to take the test. And if you're in person, I prefer that you take the test in person. And if you want to take it in person and you're normally online, you can take it in person as well. And if Thursday is a bad day for you to take it remotely, just email me. Any questions or anything about midterms or logistics? So now we'll do geometry. So if you're in class, oh, my bad. Sorry, I had music going for everyone online, my warm-up music. But we can't hear it in person. All right, sorry about that. So if you're in class, I'm going to hand out a handout. And then if you're online, I'll put it in the chat. Oh, I forgot. You guys didn't tell me I don't have my projector going. You guys are just like looking at me.
I thought you knew that.
I did not. It was like 1,000 things I have to do every day. Every thousands of buttons it feels like I have to press.
How many of those are autonomous functions of the brain, like breathing, blood circulation?
Not enough.
Imagine if you had to do all those manually.
Yeah, I'd definitely be dead. Come on. Okay, there it goes. That's what happens when I attend a meeting right before this. All right, so now we're going to go through these different groups and kind of see their typical compounds. And then we also have kind of like this shapes thing, but we'll break this down because you don't have to know all your shapes. So let's start with group 4. And so group 4, we're just looking at compounds, what these tend to look like. So kind of our classic example is going to be methane. And so methane has this tetrahedral geometry. And then so you can kind of find it on your chart. We can look at how to read this thing. So you have this key on the side. And so when it says electron pairs, this could either be atoms that it is bonded to, or if it has lone pairs, each lone pair is an electron pair. So then if we go down, so we look at methane. So our central atom has 4 different atoms attached to it, so 4 electron groups. So then if we pull up our little handout, go down to 4 electron pairs, and then this next thing, so it tells you the shape based on how many of these electron pairs are either what they define as bonding pairs, so basically bonded to atoms, versus lone pairs. So if you look at this next geometry, which we'll cover, you essentially just swap out one of these atoms and instead have a lone pair. And then they have their names. So again, if you have atoms everywhere, then it's called tetrahedral geometry. And then so the other thing to note is, so the angles, your bond angle, and it's written up here, it's going to be 109.5 for all those angles. And then, so just as an FYI, so other compounds follow the same kind of pattern and structure in this group. So, for example, silicon tetrachloride, that would look similar in structure. And you could do silicon tetrafluoride, tetrabromide, and then germanium, same thing. So germanium tetrabromide, right? Arsenic tetrafluoride, kind of, etc. So that's the classic example there. And then, so group 5, so now group 5 is going to be nitrogen, phosphorus, and arsenic. Oops. Sorry, I should have made this 10 tetrafluoride. I put arsenic in the wrong group. So 10 tetrafluoride. So arsenic's in group 5. And so arsenic, and let's start with kind of the classic example. So the classic example would be ammonia. So ammonia, if we draw out, right, it's Lewis dot structure. We said nitrogen likes to make 3 bonds. So then we can draw out the geometry. And again, we know from our cheat sheet, so it's still in the 4-electron pair group. So it has 3 substituents, 1 lone pair, but now its geometry is trigonal pyramidal. And then, so if you notice, your bond angle is also a little bit smaller. So those lone pairs occupy more space than just an atom, so they have greater repulsion. So in here, again, more repulsion from your lone pairs. So that means that this bond angle is just a little bit smaller compared to your normal tetrahedral. So this is about 107 now degrees. I don't know why I put Celsius. And so again, many group 5 compounds would follow this. So arsenic trihydride, phosphorus trichloride. But now let's look. So in group 5, you can have what are called expanded octets. And so expanded octets only apply to kind of this 3rd row and down. And textbooks always say this erroneously. They always say, oh, they start on the 3rd row because they invoke d orbitals in bonding. And so that's not true. So they don't invoke any d orbitals in bonding. So anytime it says that, that's just incorrect. And so why nitrogen can't form 5 bonds to it is just, it's simply too small. And so, for example, so PF5 does exist. So phosphorus pentachloride. And so this is what its structure would look like. But if you were to try to make nitrogen, so what you would find, and I can't remember if they've isolated it at all, like in the gas state, or just looked at this theoretically, but basically the fluorine bonds would have to be elongated. And so it would not actually be symmetrical. And so again, this nitrogen is pretty crowded, so it's not really as stable. So I'll just put not stable, can't really fit it. And so that's the only reason why, again, that we would consider that this nitrogen pentafluoride does not exist, while phosphorus pentachloride is pretty stable. And so that means, right, anything below, so phosphorus and below can do this expanded octets, and they can make several bonds. We also saw with our polyatomics, right, we could have phosphate, so that was PO4, 3 minus, So then we might have phosphorus in this sort of bonding scenario. So 5 bonds, but then this geometry would actually be tetrahedral since it's still bonded to 4 things. So it doesn't matter that this is double bonded, just for its overall geometry, still tetrahedral. And then group 6, do we remember kind of what our classic group 6 example is? Any guesses? Any guesses, or everyone looked at their periodic table? For group 6, so don't look at transition metal group 6. So don't overthink it. I was just going for water there, right? Oxygen's our first one on the row. Yeah. Where's my section? And so, right, we said that group 6, these like to make 2 bonds. So oxygen has its 2 lone pairs. So sulfur, again, would be similar. So this is what is smelly. So that's what they put in gas, so natural gas to make it smelly. And then if we look at our shape chart again, so notice it's still in the 4 electron pair group. We go back, right? 2 lone pairs plus 2 atoms, so 4. And then, okay, now we have to find this geometry where we have 2 lone pairs, 2 substituents. And then, as you might imagine, so now we have 2 lone pairs, right, occupying even more space. So this angle gets even smaller. So now it's 104.5 there. And so this is called bent for the geometry. And so again, they would follow a lot of the same pattern. But then we could also have expanded octets for group 6. So again, I would not expect to see any compounds with oxygen and 6 things attached to it. Oxygen is just too small. But SF6, that's a known compound. So SF6. Anybody know what SF6 could be used for fun? So it's basically the opposite of helium. So you know how if you breathe in helium, it makes your voice high? Well, if you breathe in SF6, it would make your voice pitched a lot lower now. Personally, I'm a little afraid of like breathing in those gases just because you could breathe in too much, even with helium. But plenty of people do it. That's just my personal preference. So there's our SF6 model here.
Sulfur hexafluoride?
Yeah, hexa.
Hexa.
Yeah, sulfur hexafluoride, exactly. Don't forget all your electrons on there. And then we can go figure out its shape. So now it has 6 electron pairs, and so this is a fairly classic octahedral example. And so selenium, tellurium, those again can do expanded octets. You could also, let's see if you could figure this one, what this structure might look like. So if I give you SF4 now, so what might that look like? And so make sure you total up how many electrons you have. So see if you can come up with a structure. How many lone pairs does it have?
Square planar? Oh, wait, no, not expanded octet, no. So,
So think silently for a little bit, draw it out, count the electrons. So what do we get for possible, at least a structure? We don't have to identify the geometry, but how many bonds, how many lone pairs? Do we remember our bookkeeping method too? And we want to add up all our total number of electrons and so do we have any possible structures or? Yeah, what do you have?
tetrahedral, 4 electron pair.
So let's just look at this. Okay, so we have it attached to 4 things. And then all of these fluorines, right, should have an octet. Is that what you did? And so this is a good start, right? So I always encourage people to, with these structures, is that you should just kind of start somewhere. And then, you know, really the question is, like, can you then analyze your structure, you know, go through the checks, and then you can kind of fix your structure yourself. And so this is pretty good. But let's see if we have the right total number of electrons. So how many does sulfur contribute? So how many valence electrons? So 6. And then fluorine how many valence electrons does 1 have? So 7 times 4, so this is 28 plus 6 there, so that's 34 electrons, right? And then, so I'll just do some quick math here. So each one of these fluorines has 8 with them. So 8 times 4. So it looks like we're at 32. And so we're missing 2, right? And so let's just stick them on the central atom then. So that's the most likely thing. So we're not going to stick them on fluorine. They already have an octet. But we do have to bring the correct number of electrons to our party. So let's go ahead and do that. So I'll draw my lone pair on sulfur. And so now this looks good. So we can kind of analyze our structure. So the fluorines all have the octet. It's okay that sulfur feels a lot of electrons. So it feels 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But we said that that's okay. It can do expanded octets, so 10 electron total for sulfur. And then, so now we could also go about and identify the geometry. So we have 4 things attached to it plus 1 lone pair. So what electron pair group does that put us in? 5. So 5. So if we look at 5, and then so skip over to 4 bonding pairs, 1 lone pair. And so this is called either the sawhorse, or sometimes you see seesaw geometry. Since if you kind of turn it like that, it'll look just like a little seesaw with these 2 fluorines kind of going in and out of the plane of the board, the other fluorines acting as your little seesaw. So you could reorient it as well. So we'll do more practice with drawing structures. All right, so octahedral and seesaw, those are kind of the more common ones for group 6. So let's look at group 7. So group 7 typically just makes 1 bond unless we're doing funky expanded octets. So we've seen this, and let's just take aluminum chloride. So actually, this is a funny compound. So what type of compound do you think aluminum chloride is? Ionic or covalent? So I did draw it as covalent. Would you expect it as such, or? And it is covalent, but.
Well, I was just looking at it being non-metals. Or wait, aluminum's a metal, isn't it?
Yeah.
Yeah, that's why it's funky. So if this comes up in naming too, like you could argue, yeah. It's supposed to be a covalent compound. So that's what you kind of find with these bonding scenarios, is there's some funky things. So you could argue that it's an ionic compound just because it's a metal plus a non-metal. We'd have to do the electronegativity check. But if you look at it in the solid state, which is kind of what matters and what chemists care about, it is a covalent compound. And so in the case of like aluminum trichloride, it actually makes this bonded structure, and it would have a trigonal planar geometry. So that's a little odd. And let's see what, obviously boron trichloride is kind of the same issue. So you have a covalent compound there. Just while we're on the topic of funny exceptions, beryllium dichloride is also an exception, or beryllium chloride, depending on how you name it. So if you look at it again in the solid state structure, you would totally expect it to be an ionic compound, but apparently, according to the solid state, it has kind of more covalent character. And then, so let's look at kind of some funky geometries that halogens can do. So again, fluorine's pretty small, so you're not going to see it do funky expanded things. And then even chlorine and bromine don't do as much, but iodine can be weird. So take a minute or so and see if you can figure out what II3 would look like. And of course, you could also sub in like IF3, IBr3. Question?
Oh, no, no, I just think I got it.
All right, so what do we get for a structure? How many things are attached to it? Yeah,
Okay, so there would be 5 as 3 fluorine and 2 electron pairs, as there's a total of 28 electrons. The fluorines can all hold 8, which brings it to 24, so that would mean there are 4 lone electrons left. So there would have to be 2 pairs remaining. So it would have to be like that in a T-shape.
that sounds good. So did everybody do that, follow that? So let's kind of go through that. And it didn't matter, right? He did fluorines, you could pick iodine, bromine. Doesn't matter. So they all have,
Iodine.
I just say iodide if it's like in the last part of the name.
No, I mean you said there's 3 iodine, iodide, triiodide, but I'm saying that's what the first one was, right?
Yeah,
Okay.
you could have picked the fluorides or bromides. But basically, right, so they all had 7 valence electrons. So I think that's what you said, right? You got 28 total. And so if you just kind of stuck 3 bonds right? So you start with your central atom, just start making a line to each of your substituents, fill in your electrons right on your other iodines. Then that gave you 24, so then just like you said, figured you needed 2 more lone pairs, and then usually just put them on the central atom. And so now we know we're in electron group 5, so 1, 2, 3, 4, 5. And so that gives us that T-shaped geometry. Wrong T-shaped, T-shaped. So let's look at group 8. So, you know, we've just finished saying that the noble gases don't really react, but xenon does tend to make some compounds. And so see if you can figure out what xenon difluoride looks like, and then also xenon tetrafluoride. So those are the 2 most common ones. So take a few minutes, count up your total number of valence electrons, make sure everyone is coming to the party. So do we have a guess for at least xenon difluoride? And looking in the chat too. Yeah.
So I believe it would be a linear 5-electron pair.
So linear 5-electron pair. So that means 2 substituents and then 3 lone pairs, right? And so again, there's a couple of different ways to look at it. So you could either think back, so you know xenon has 8 valence electrons, and so 2 of those are involved in bonding with our fluorine, and then that means the other 6 are just hanging out as lone pairs. You could also add up your total number of electrons, so you have 8 plus 14, and so that gives you 22. So you could count up, so 8 plus 8 is 16, 17, 18, 19, 20, 21, 22. So again, that's how you get your 3 lone pairs. And then, yep, just like you said, it would be linear. So we double check ourselves, 5 electron pair, go over to 3 lone pairs, giving us linear. And then we could also count up all our electrons. Of course, the fluorines are satisfied by the octet rule. And then xenon has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total electrons that it feels. So go ahead, take another minute or so. So what is the xenon tetrafluoride? So we'll give everyone a minute, or until 38 or so.
What did you call the first one?
Xenon difluoride.
No, like was it linear?
Yeah. So that one, if you go over to your 5 electron pair group, and then 2 bonding things, 3 lone pairs.
So you just say it has a linear.
Yeah, linear geometry.
Okay.
Since when you just look at it, right, it's just xenon and 2 fluorines, you're not really like seeing the electron clouds. So how does our xenon tetrafluoride look? Yeah.
Would it be a square planar?
Yep. So then how many lone pairs does it have?
2.
Yep. So 2. And so again, you could go through the same process, either thinking, okay, xenon has 8 valence electrons, 4 of those go in bonding, so that leaves me 4 non-bonding. You could total up the number of electrons, so xenon had 8. 7 times 4 is 28. So 36 total electrons, so 4 times 8 is 32, 33, 34, 35, 36. So either way, you should get this structure. And so you said that it was square planar. And so I don't know, I assume you use the chart, and so we can find our 6 electron pairs and then go over to our square planar. Right, so good job with all those geometries. And then so for our class, we'll just kind of focus on these ones. And so I just wanted to do a few more examples. So see if you can come up with the structure for H2CO. So what would that look like? So any thoughts on what this looks like? So I tried giving you a hint by putting it with this trigonal planar category. But let's see how it is trigonal planar. So we have carbon, and again, just kind of playing with it. So I'm just thinking in my mind, well, carbon likes to make 4 bonds. So it might be a good central atom since oxygen typically just makes 2, each hydrogen just makes 1. And then from there, right, you can kind of piece together, well, I know oxygen needs 2. And then your total electrons should still all add up. So 2, right, 1 from each hydrogen, plus 4, plus 6. So we should have 12 electrons in our system. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then, so it still works out for our little chart. So for our bonding pairs, looking at our central atom, so again, carbon, it's bonded to 1, 2, 3 things. So then we can look at our chart. So 3 electron pairs, so 3 bonding pairs still gives us trigonal planar. And I like the answer drawn out in the chat, trying to show that double bond. Did you have a question?
Oh, no, I just think I figured, no, I was just raising this, I think I figured it out.
And so let's look at other trigonal planar geometries that you might see. So this is good. I don't know if any of you will go on to take OChem. I know it's hard to type in the chat. If Zoom's whiteboard feature ever worked, then I would use it. So let's look at this other molecule. So first I'll draw it how an organic chemist would draw it, then we'll kind of translate it. I draw terribly. So this is benzene. So that's how you would normally just see it in a textbook. You may also just see it like this. So all this means is you have what's called an aromatic system. So meaning these little double bonds can just kind of move around. So they can move around there. So that would move those double bonds, move that double bond. And since you can just do that over and over and over again, such that this is a delocalized, basically, ring of electrons, they abbreviate it like this. But let's break it down a little bit clearer. So if you recall, each one of these points represents a carbon. So let me just draw kind of 6 carbon points out. And then, so again, we have these alternating double bonds. So I'll just kind of alternate now, like double and single bonds. And then remember we said each carbon has to have 4 bonds. So again, with this organic chemistry structure, we want to draw out now all the hydrogens. And so this is what I would say the super explicit way to draw it. You could also, just kind of add in your hydrogens to this structure if that helps. But either way, what I'm kind of getting at is so we can tell the geometry of this. So again, looking at our central carbon here. So it's attached to 1, 2, 3 things. So this is telling us that, again, we're going to have this trigonal planar geometry, and that's going to be true at each carbon. And so this is telling you that benzene is flat, and indeed, that is true. So I was just going to pull up benzene. So this is just benzene, again, what it looks like. And you can tell that it's planar. So you can get a lot of information just with these little Lewis dot structures and are drawing them, we can figure out geometry and all sorts of things. All right, so we haven't quite gone over polyatomics. So let's look at this together. So let's look at now the sulfate polyatomic and see if we can figure out what its geometry looks like. And so same rules apply, right? We want to figure out how many electrons are coming to the party. So we know sulfur has 6, so 6 valence electrons. Oxygen has 6 as well. There are 4 of them, so 24 there. And then if we have a -2, that means we're adding electrons. And so I kind of put it, again, for bookkeeping purposes, I put what the charge is, and then since it's -2, I know I'm adding 2 electrons. So now I'll just add it. If I had a plus charge, right, I would do a subtraction. Oh, so erase. And so let's see, let's add them. So 6 plus 24 is 30 plus 2, so it looks like we're at 32 electrons. And so again, you can just kind of start drawing bonds to things. And this is, again, I will encourage there are no necessarily wrong structures. So we could start with this. And so let me see. So 32 electrons. So this is looking good. I'll fill in all the electrons now to give everyone an octet. All right, so that's all satisfied. So let's look at how to analyze the structure, because we haven't learned fully how to analyze a structure. So far we've learned, okay, I at least need to have my total number of electrons correct. And then, so the next thing is we need to talk about kind of formal charges. How do we calculate them? And then how do we use them to tell if it's a good structure? And so let's just define kind of our formula for formal charge. So formal charge is just equal to, so the number of valence electrons, so right from your periodic table, so whatever the number of valence electrons is, and then minus, I say the number of bonds, and then minus the number of individual atoms. And so let's go through this analysis together. So if we're looking at our oxygen here, and we'll just plug it into the formula so you don't have to write it out every time. Once you get the hang of it, you can just indicate your charges. But looking at oxygen, and it doesn't matter which one we do in this case, they're all the same. As in, right, they all have 6 electrons on them, 1 bond. So let's go through its formal charge. So we have 6, again, just from periodic table. So oxygen has 6 valence electrons, minus, so we have 1 bond, and then minus, they all have 6 atoms, or I didn't mean to put atoms. I should have said electrons. Apologize. So counting up those electrons. And so this gives us a -1 formal charge. So we'd have a -1 charge for all our oxygens. And then so our next rule is all these formal charges have to add up to the correct charge. So we've been mainly dealing with neutral atoms, so it hasn't really mattered. So let's check our sulfur charge. So let's do sulfur. So sulfur still has 6 valence electrons. And then minus, so sulfur has 1, 2, 3, 4 bonds. No individual electrons on there. And so that leaves it with a 2+ charge. So write that on there. And then, so kind of our next rule of evaluating structures is we want to minimize formal charges, and we also want at least try to get the negative charge on the most electronegative atom. So in this case, we kind of have this issue of we have this 2+ charge on sulfur and all these -1 charges on oxygen. So there might be another way to write this structure. And so these are just called resonance structures. And what you'll kind of realize is you need like all the average of your resonance structures to give you the full picture. But so let's point out a few things before we draw our resonance structure. So notice tetrahedral geometry. So this sulfate, right? Sulfur bonded to 4 things. So this matches with tetrahedral, so that's fine. And so now let's see if we can draw some resonance structures. And so to draw resonance structures, you're just moving electrons around. So we're not going to change the connectivity. We're not going to do anything funky. And I'm going to show the arrow pushing in case you do go to OChem. But all we're going to do is we're going to take these 2 electrons, and then we're going to turn them into a bonding pair. And then we can probably do the same for this one as well, and that will get rid of our 2+ charge there. So now we can just rewrite our new structure. And so now I'll draw sulfur. And so it doesn't matter which oxygens you turn from single into double bonds. And then again, you want to keep your correct number of electrons. Bless you. And so we still should have 32. And so that looks to be the case. So 8, 8, 8, 8. Now we've minimized our formal charges, so we still have, right, -1 formal charges on these oxygens, which makes sense since we have to get to -2 total for this sulfate. But now we've worked to, again, minimize our charges on the rest of these. Of course, now the only issue is, so if we go back, right, sulfur had a nice octet rule here, so that was satisfied. And now with these 2 double bonds, so sulfur is neutral, but now it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it gets 12 total electrons, which isn't horrible. Again, we said sulfur can be hypervalent, so this is okay. But again, you're kind of getting the average picture with these resonance structures. And then what you would want to do for completion's sake on an exam is write out like all the structures with the appropriate formal charges. And then so you can kind of tell that you have kind of this average bond, so you could add up all the bonds and kind of get your average bond there. So does that make sense? Is everyone completely confused or following along? And then so just looking at another classic tetrahedral structure before we move on. I think we mentioned it before, but it's worth mentioning again. So ammonium, we mentioned that was one of our few cations, and thanks, chat, for saying that you think you're following along. I appreciate the feedback. And so this would also adopt a tetrahedral geometry. And so let's go through the formal electron counting. So nitrogen, 5 valence electrons. Hydrogen, 1 valence electron times 4. now we're at 9. And then we have a plus charge, so I'm going to put a plus there, which means we're going to subtract an electron, right, because it's positive. And so now we can add them. Oops, I did some premature adding. So 5 plus 4 is 9 minus 1, so that gives us 8 electrons. So then we can draw out our structure. So again, just starting, I would just draw one bond to every hydrogen. And so that gives us, right, our structure. So it's tetrahedral, 8 electrons. And then the one thing is we have to have our formal charge somewhere. So it's not on hydrogen, so you can kind of mentally do it. Okay, 1 valence electron minus 1 bond. But now let's look at nitrogen. So nitrogen's formal charge. So it has 5 valence electrons minus 1, 2, 3, 4 bonds minus no electrons on there. And so that's where your 1 plus formal charge is hiding, is on that nitrogen. So then you just want to indicate it, drawing your little plus sign there to show your formal charges. Let's see. So looking for good examples of trigonal pyramidal, other than ammonia, of course. We've kind of beaten ammonium. So here's a funky one I think you can try. So figure out what sulfite looks like. So SO3, 2 minus. So take a few minutes, draw it out. What's its geometry? So did we get a structure for sulfite? How many bonds? How many lone pairs? Also start with how many total electrons. Oh, I added wrong. So did we get 26 total electrons at least? So 26 electrons, and then how could you play with them? So you could start just with kind of what I say the simplest structure. So slap sulfur in the center, right? Attach on 3 oxygens, and then just kind of see where you're at. And so 8 times 3, so that gives us 24. So we're 2 short, right? So I'd probably just put those on there for now. So this looks at least somewhat decent of a start. So did people get kind of this at least maybe as a starting point, or? And then so if you did your analysis, so do our formal charge analysis. So what's our formal charge for all these oxygens?
-1.
So -1, right? Because we have 6 valence electrons minus 1 bond minus 6. So that gives us -1. And then the whole thing has to equal to 2 minus. So we could either do some math to figure out what this charge is, or if we calculate our formal charge for sulfur. So we have, right, 5 minus 3, or not 5, 6, sorry. 6 minus 3 minus 2, that gives you 1 plus, right? And so again, this is a good structure. So thanks, Chet. I see we're following along. But then we could draw a double bond to eliminate the structure. So again, this would be 1 resonance structure. But then we'd want to draw our other resonance structures to show that we know they also exist. So now, just filling in the electrons, because all we did, I just moved one of those down into bonding. So we still have our 26 electrons. And then for completion's sake, you'd want to draw the other ones. We can draw a formal charge. So now we just have negative charges on the oxygen. So we've minimized that as well. So now I'm just drawing resonance structures. And so we use these double-headed arrows too to show that they're resonance structures. So again, just moving electrons around, not changing the connectivity or anything. And so sulfur, right now it has 10 total electrons, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's okay for our expanded octet. And then so what's our geometry here?
Triagonal. Oh. What? No, triagonal parallel.
Yeah,
Yeah, triagonal parallel. Oh,
Yep.
sorry, I was confused slightly because it was showing that,
sorry.
and that just didn't.
I was trying to move it down so it'd be out of our way, this one bent. Come on. But yes, it is under our trigonal pyramidal, and then you can see that it fits. So again, central atom with 3 bonding pairs, 1 lone pair. And so that puts us back in our trigonal pyramidal geometry. And sorry, I'm trying to come up with some good bent ones because I wanted to show you. Well, let's look up actually. So we already covered kind of the classic examples. Also running out of time here. But we could also look, so if we had, let's just say methanol, right? This would also adopt a bent structure around that oxygen. That's what methanol would look like in 3D. But now let's also talk about another concept of polarity, which is pretty related to our shapes. And so let's compare for a second carbon tetrachloride versus dichloromethane and see if we can determine who's polar, who's non-polar. And so if you're trying to look to see if something is polar or not, you're basically trying to see, do I have a break in symmetry? And then is that break in symmetry, does that mean that kind of one side has more electron density than the other? So what I mean by that is, okay, if we compare carbon tetrachloride here. So carbon tetrachloride, it's tetrahedral, and then we could rotate it such that it's symmetric, right? We can flip it. We can do all sorts of things to make these chlorines be in the same position. So this is fully symmetric. And what this also means, so yes, each individual chlorine is pulling electron density towards it. So I'm drawing these arrows, and I'm drawing them in kind of the chemistry, again, notation. And so I put a little plus sign on my tail, so you can tell like this is the positive side. The arrow is showing where the electrons are being pulled towards, so this is opposite from some physics conventions. But basically, it's being pulled out evenly in all four directions, so such that it cancels out. And so this molecule, carbon tetrachloride, would actually be considered nonpolar. And then if we compare it to, so this is DCM or dichloromethane. So if we look at DCM, so we have these chlorines, and they're again pulling that electron density towards it. And so if we look at this molecule, we would have this one side that has a large electron density on it, right? So it has like a large cloud over here. Meanwhile, this would have a small cloud. And so we would say that DCM is polar. And so again, we do have a break in symmetry. So it's not symmetric by rotation. And so again, you have kind of this polar side. So again, you're looking for lopsidedness to your molecule. So going back to this example, so this would also be polar since you have oxygen on one side, that's electronegative. So looking at, oops, I drew ethanol. I meant to draw methanol. But both of them, right, methanol, ethanol, so those are, again, both polar since they have kind of OH on one side. And then, so water would also be polar. So it has this one side with electron density on it. Look at your homework. so I don't want to spoil all of them, but like ammonia. So do you think ammonia, would this be polar or non-polar? So is it symmetric all the way around, or does it have electron density on one side? So I see a polar in the chat, so that would be correct, right? You have these, the two lone pairs on this one side, so this side is, again, very electronegative. It has all our electron density, so this would be polar. You would actually find that ammonia can like react from this nitrogen. It can bind to metals from those two lone pairs. Let's look at another one. What about CO2? So the way I drew it should help. Exactly, so nonpolar. So this usually confuses students because you see, right, an oxygen, and usually if we see a CO, at least in the form of a carbonyl, right, that's polar. But now in this case, you have an oxygen on each side, so they cancel each other out, so it's more nonpolar. So what about BF3? Polar, nonpolar? What do we think? So I think I see nonpolar in the chat. So right, BF3, it's that trigonal planar, so you could distribute those fluorines evenly all the way around. They're symmetric by rotation. So yeah, this would be nonpolar. And then let's try this one from your homework. So Cl2O. So how would you name it? Is it polar, nonpolar? Can you draw a structure? What does your structure look like, or what is its name too? So here in the chat, I think it's polar because it has two sets of lone pairs. So I like that. So it should look kind of like water, right? And this is kind of funky, but chlorine likes to make one bond oxygen, right, makes 2. And so we have this dichlorine monoxide, for our compound. And then just like the chat said, so we still have our 2 lone pairs on here. And so this would make it polar. So again, we have this unevenness from our lone pairs, and of course our chlorines are also electronegative, but either way, it is polar. All right. Any questions or anything from this chapter? So I think we pretty much hit it all, so we'll probably end lecture here for today. So that should cover chapter 4. And then so Thursday we can start reviewing for our midterm, which will be, again, next Thursday. So come with plenty of questions, and we'll just work out some practice problems together, just kind of practicing everything, making sure we're all on the same page. So you can grab homework if you didn't already. And then I do have the labs printed out, and so I'll see many of you in lab at 7 p.m. Otherwise, everything should be online. And then just make sure you're turning in labs to Gradescope. And then I'll hang around on stream. Yeah, Tuesday will also be a review. So we're going to do review Thursday, and then next Tuesday, making sure everyone feels really good for the midterm. And yeah, you can put it there.
There we go.
All right, thank you all for participating in the chat. I appreciate it, following along and answering. So I'll see some of you in lab. Otherwise, I'll see you all by email or Zoom. Yeah, that's our lab for this week. Yeah, you can put it on that pile. You want to throw it on the pile?
Oh, nothing. No. I was just doubting my own work for a second before I realized.
All right, thanks again. I'm going to stop